Greetings, mathophiles. Welcome to a video on a technique called implicit differentiation, which is occasionally convenient and sometimes necessary for finding derivatives when you're in a situation where you don't want to or possibly can't solve a relation for the dependent variable. This technique is also the basis for an application called related rates that we will delve into at another time. On your screen, you'll see a graph of the unit circle, and our task is to find the equation of the line tangent to the unit circle at the point √3/2, 1/2. And the first thing you may want to do is to convince yourself that that point is on the circle, and so if you would like to do that, you can pause the video and briefly make that exploration. All right. I'm going to claim that anyone watching a calculus video has at least one way of approaching this problem already, and that is to recognize that a radius drawn to a point of tangency is perpendicular to the tangent line. So I'm going to turn on a couple of tangent lines. And of course, we have an interesting situation in the case of the unit circle because it is not taken as a whole a function. I can treat the top hemisphere as a function y of x. I can treat the bottom hemisphere as a function y of x, but I can't treat the entirety of the circle as a function. Fortunately, it's not necessary that we be able to do that in order to answer the question that is in front of us. We wanted to know the equation of the tangent to the circle at √3/2, 1/2, so roughly about here. And that should be doable, right? Because in the neighborhood of this point of tangency, y is a function of x, even though that's not globally the case over the entire circle. If you know some algebra, you know some geometry, you can find the equation of the radius to the point of tangency. You can then easily find the slope of the perpendicular, and using the coordinates of the point, you can make the tangent line. And if you'd like to try that for yourself, you can pause the video here as well. Those of you who know the power rule and the chain rule will be able to find the derivative and complete this problem using skills you already have. You can just take the equation of the top hemisphere and differentiate it old school, so to speak, and get the slope of your tangent line by plugging in your coordinates of your point of tangency, and you're good to go. What I want to look at now, though, is a technique that is different from the two things that we've just discussed. It's optional here, clearly, because we have a couple of other ways of approaching this question. But as we'll see, there are situations where it might be the only thing that is available to you. So we're here on the document camera, and I'm going to start with the equation of the unit circle taken as a whole, which is that x² + y² = 1. Now, locally, in the neighborhood of our point of tangency, we can treat y as a function of x, and I'm going to write that very explicitly here. x² + y of x squared = 1. Now, a little bit of algebra will tell you what that function is, but suppose we didn't know it. I know that if I differentiate on both sides of an equation, I should get a true statement, right? The derivatives of things that are equal are equal. So I'll differentiate the left-hand side with respect to x. And of course, if I differentiate x², I get 2x. If I differentiate y of x², this is a composition in which the outer function is the square. So this is going to be 2 times y of x. But then y of x is itself a function, and so we have some chain rule. And I don't know yet what the derivative of y with respect to x is, so I'll just call it dy dx. And then, of course, the derivative of a constant is 0. Now I'm in a position to solve for dy dx. So I can divide the entire equation by 2. That'll save me a little time. And so y of x dy dx equals the opposite of x, and so dy dx equals the opposite of x over y of x. That notation has sort of served its purpose already. And so I'm just going to go back to calling that y. So dy dx is op x over y. Then what is dy dx? At our point of interest, well, our point of interest was root 3 over 2, 1/2. So this will be negative root 3 over 2 over 1/2, also known as negative root 3. And so the equation of our tangent line should be y equals 1/2 minus root 3 times x minus root 3 over 2. And if you took the trouble to work this out using either geometry and algebra or old school calculus, you should find that your tangent line agrees with this one. Just for the record, here we are back on Desmos, and I'm going to highlight the tangent line equation that we just came up with. And as you can see, it's a very good fit for what we had just by sliding around and locating ourselves approximately at that point of intersection. This is not exactly root 3 over 2, 1/2, which means the correspondence isn't perfect, but I hope this is sufficient visual evidence that we got the right equation. In our first example involving the unit circle, the use of implicit differentiation was optional. We had a couple of other things we were in a position to do. Here, it's a little bit different story. I have no way of solving this equation for y and then differentiating explicitly, if you will, differentiating using old school non-implicit techniques. If you know enough about inverse functions, there is a thing that you can do as a means of approaching this, but it would be very easy for me to alter this example so that that would not be a possibility either, and then you'd have no choice but to use implicit differentiation. So we'll go ahead with this one on the theory that it's a little more typical of the sorts of situations in which you might use this technique. So I'm going to again start by rewriting my relation here, my equation, to really emphasize that I'm imagining that y is a function of x, at least locally in some place that's of interest on whatever this curve looks like. Once you have enough experience with this technique, it's probably a maneuver that you can dispense with. You can probably just continue to call it y. But as you probably know if you're watching this video, forgetting the chain rule is one of the more common errors in calculus. And so until we are really comfortable with how this process works, we probably want to continue to do this just to help us to avoid that particular mistake. So on the left-hand side, we have a product. So its derivative is going to be the first factor times the derivative of the second factor. Now, that's y squared, where y is some function. So I differentiate the square, I get 2 times whatever's inside. Then I have to multiply by the derivative of whatever was inside, and we're calling that dy dx. Then we have the second factor, which is y squared, times the derivative of the first one, which is just 1. So I'm just going to call that y of x squared because it is. And then on the right, we differentiate the cosine of something, we get the op sine of the something. And if that something was a function, we got to multiply by its derivative, so times dy dx. Now all we have to do is solve for dy dx. I'm going to make one pass where I just clean things up a little bit, and this isn't strictly necessary, but it's going to make the algebra, I think, a little more convenient. So I'm just going to go back to calling the y of x's y, now that that notation has served its purpose. So this is going to be 2xy dy dx plus y squared equal to op sine y times dy dx. Now, this is the way these things tend to come out. You have terms involving the derivative dy dx. You have terms that do not involve the derivative dy dx. And so you just haul all the terms that involve a dy dx as a factor to one side of your equation, haul all the other terms to the other side, factor and divide. So I'll hold the dy dx terms to the right. It really doesn't matter. So negative 2xy dy dx minus sine y dy dx on the right-hand side. And then we'll factor out the dy dx. You'll get to the point where you probably don't need to do this as a separate step, but for now, let's. So y squared is dy dx times up 2xy minus sine y. And so dy dx is, it's probably a little easier to do this, op y squared over 2xy plus sine y. And we were able, in this case, to find a derivative, dy dx, in a situation where we were unable to solve the original relation for y in terms of x. So it's a very powerful technique that you occasionally are forced into and that you sometimes might want to opt for as a matter of convenience, depending on the circumstances. I hope this has been enlightening. I hope it's given you some understanding of how this technique works and a start at getting proficient with it. Happy mathing.